Let's see. Yeah, no, I think it's recording. Perfect. All right, so what's this measures of spread? So the idea is the following. So these measures of spread, they're gonna describe how similar or varied the set of data values, okay? So they're gonna show how much the values differ from the mean, okay? So we'll see, we're gonna try to describe and see if there are a lot of variation in the data values, or like the data values would be like are more constant. Okay, so yeah, so let me just write down what I just said. So measures of spread or measures of variation. So so these measures, they describe how much or how similar, let's say, so how similar or varied the set of data values, the set of data values. Okay. So in other words, they're gonna show how much the values differ from the mean, right? The mean, they're supposed to be like your average, is supposed to describe your data set. And so these measures, so in other words, so these measures of spread, they show how much the values, the data values, of course, the data values differ from the mean. Okay, so let me give you a couple of examples, so then you can understand what I'm talking about here. Okay, so first example, I'm gonna go with the flower diameters. So example 1. Okay. So let's say we have a random sample of a flower diameters. Let's say we have 6 flowers. So a random sample of flower diameters. Bless you. In inches, let's say. I'm gonna use the inches, all right? And so let's say you have like 2 different hybrids of flowers. So first hybrid, first type of flowers, hybrid A. The first type of flowers, hybrid A. So let's say we have 6 flowers, and so the first flower, let's say its diameter is 2 inches. Second flower, 3 inches. 3 inches. Fourth flower, 8 inches. Fifth flower, its diameter it's 10 inches, and then last one, it's 10. All right. So anyway, so the idea here, so we have 6 flowers, right, in this hybrid A. Okay. The second type of flowers, hybrid B. Hybrid B. So we have, let's say, first flower has diameter of 5 inches, second same, third the same, 5 inches as diameter. Fourth flower has 6 inches as diameter, 7, and then 8. Okay, so again, we have also 6 flowers. All right. So I mean, of course, we can compute the mean of the 2 hybrids. So for the hybrid A, so like for the hybrid A, so let's just first compute I'm gonna compute the mean of the two hybrids, okay? So compute the mean diameter, okay? So for the hybrid A, for the first type of flowers, the hybrid A, so the mean diameter would be equal to the sum of the diameters. So it's like 2 plus the plus 8 plus 10 plus 10
Excuse
over,
me.
yes,
A random sample of what?
sample of flower
Oh,
A.
okay.
That's
Thank you.
right. Mhm. This is flower. Sure. Flower. Flower diameters. And we have like two types of flowers, right? Hybrid A and this, and let's say another hybrid B. Okay. For the hybrid A, the mean diameter. So so it's the sum of the diameters over. Of course, we divide by the size of the sample. We have 6 flowers, so we're gonna divide by 6, right? So the mean would be equal to, so like the top, it's I think 36, right? The top would be 36 here over 6. So the mean is 6 inches, right? 6 inches. So X bar is 6 inches. So the hybrid A, the mean diameter is 6 inches. Now for the hybrid B, the mean diameter would be, so the sum of the diameters, it's like 5, plus 5, plus 5, plus 6, plus 7, plus 8 over 6. So the top would be like 15, 21, 28 plus 8, that would be 36 again over 6. So that's equal to 6. So the thing here, guys, so both hybrids, they have the same diameter mean, right? So mean diameter. So this is the mean diameter here. So the mean diameter here, X bar, it's also 6 inches. Okay, so both hybrids, they have the same mean diameter, right? Both mean is equal to 6. But the thing is, if you compare the diameters of the two hybrids, like for the first one, as you can see here, the first hybrid has like more variations compared to the hybrid B. Okay, so the hybrid B is more constant. You see the higher diameter, in the hybrid B, it's like the numbers, the values are very close to each other, right? You have like 5, 6, 7, 8, right? So the numbers are more or less the same thing, right? They are very close to each other, right? In the hybrid B. But then hybrid A, it's more varied, right? There's more, it's more, you have more variation in the hybrid A, because as you can see, it goes from like 2, the smallest diameter is like 2, and the highest diameter is like 10. For the hybrid B, the smallest diameter is 5, and the largest diameter is 8. Okay, so you have more variation in the diameter in the hybrid B, in the hybrid A compared to the hybrid B. So yeah, so hybrid A has more variation, right? So hybrid A, oops. So hybrid A has more variation. Okay. The hybrid B is more constant. I mean, the diameter, the hybrid B is more constant. Is more constant. Again, what I mean by more constant is, the diameters are more or less close to the same number, right? Like in the hybrid B, as you can see, I mean, the numbers, they go from 5 to 8. Okay, so the difference between 5 and 8 is it's like just a 3, right? So you see here the difference between the largest and the smallest values, it's just a 3. Here in the top, the difference between the largest and the smallest diameters, it's like 10 minus 2, which is 8. Okay. So so in other words, the values, the data values in hybrid A are more varied than the data values in the hybrid B. Okay, so the values, the data values in hybrid A is more varied than data values in hybrid B. Charlene, yeah, no problem. I got you. Thank you.
Excuse me,
so
I can see.
you can see the top, the bottom.
Yeah, thank you.
Mm-hmm. So you see what I'm saying, guys? You see the values in the hybrid B, they are very close to each other, like from 5 to 8. So that's what I mean here by when I say like hybrid B is more constant, right? The numbers are kind of, they're not really different from each other, right? So they're very close to each other. Okay. Does this make sense to you? I mean, I can give you another example. All right, so let's have another example. So this is first example 1, example 2. All right, so let's say we have 2 data sets. Okay, so we have the first, let's say first data set. First data set. Let's say we have the following values: 1, 2, 20, and then 38, and then like 39. Okay. Second data set, it's, let's say, like 18, 19, 20, 21, 22. All right. So what will be your guess, guys? Which set or which data set is more dispersed than the other one?
The first data set.
Excuse me?
First data set.
The first data set, absolutely, is more dispersed than the second data set, absolutely. So very good. So the first data set is more dispersed than the second one. That's because, well, as you can see, like for the first data set, you know, the smallest and the largest data values, the difference between the smallest and the largest one, it's like 39 minus 1, that would be 38, right? So here it's like the difference between the largest and smallest one will be 38. In the second data set, the difference between the largest value and the smallest value, it's just 22 minus 18, that will be 4, right? So the numbers in the second data set are very close to each other, right, compared to the first one. Okay, so yeah, so the first data set has more variation than the second data set. So the second data set is more constant because in the second data set, as I said, it's the numbers that are close to each other, so they're more or less the same thing. Okay, they're very close, right? So yes, yeah, so let me just write down what I just said. So first data set has more variation. First data set has more variation. The second is more constant. Okay, in the sense that numbers or values are close, are not that are close to each other. Okay. Now, I mean, if you compute the mean of the first data set and you compare to the mean of the second data set, actually they're going to have the same mean. Okay, so like the mean, so if you compute the mean, so the x bar of the average of the first data set would be like, we have 5 numbers. So it's like 1 plus 2 plus 30, plus 20. Yeah, so 1 plus 2 plus 20 plus 38 plus 39 divided by the size of the sample, of course, by 5, because we have 5 numbers. Anyway, so the top actually, I think, would be 100 divided by 5. So the mean of the first data set would be 20. That's the average of the first data set. Okay, and X bar of the second data set. So it's going to be like, 18 plus 19 plus 20, 21, 22 over the size of the sample. Again, it's 5 numbers. So it's at the top again is going to be 100, right, over 5. So X bar of the second set. So both data sets have the same mean. Okay, and again, the mean is supposed to represent the expected value of your data value. I mean, for your data set, right? So the X bar of your data set, it's also 20. Okay. So the expected value for both data sets, it's 20. But the thing is, one data set is more dispersed than the other one, right? So yeah, so so we're going to use the measures of spread to see how much the values differ, the data values differ from the mean. Okay, so the idea is so both they have the same mean, both data sets have the same mean. However, of course, the first one is more dispersed. Is more dispersed than the second one. Than the second one. Okay, so the measures of variation, guys, of measure of spread, they're gonna help us to better understand the data. Okay, because here, as you can see, the mean, both data sets, they have the same mean. However, they have like different variation, right? The one is more dispersed than the other one. So the measures. So the idea is that we're going to use these measures of variation to have a better understanding of the data. Okay, so measures of variation, they're going to help us to understand, to have a better, understand the data. understand the data. Okay. Well, I hope this makes sense to you guys, right? So that's our goal today. We're gonna see a couple of measures of variation. And with these measures of variation, we're gonna try to describe how similar or varied the set of data values. Any questions so far? All right, so that's for the example. Now, the first measure of variation, which is kind of very simple, but it's not really effective. Let's see this. So first measure of variation is called the range. Okay. So, I mean, the range of a data set is just the difference between the largest and the smallest values. Okay. So the range of a data set is just the difference between the smallest and largest values. Is the difference between the largest and the smallest data values. Okay, so like in our previous example, you know, you had this, so first data set was like, so it was like, I think 1, 2, 20, you know, 38, and then 39. Okay. Anyway, so we said that the average or the mean of this, first data set is 20. Now the range, what would be the range in this case of this data set? Well, it's just, so the range, it's just the difference between largest and the smallest data values, right? So the range here in this case would be like, so of course the largest value here, it's 39, and the smallest one, it's 1, right? So the range would be 39 minus 1, that would be 38. Okay, so that's the range of the first data set. Now, second data set, so we had on the second data set, we had like, I think first value was like 18, and then 19, then 20, 21, 22, right? So the range in this case would be like, so the range in this case would be like 22, that's the largest value, of course, minus the smallest one. So that's 22 minus 18, that would be 4. Okay. So of course, the range of the first data set is larger than the range of the second data set, right? So in other words, like the first data set is more dispersed than the second data set. Okay, so the range, so the range of the first data set is larger. Okay, then second one, the range of the second one. The second data set. Okay, so the range is 38, the second it's 4. Okay, and of course 38, it's larger than 4. So what we can conclude in this case is that the first data set. So the conclusion is that the first data set is more dispersed. Is more dispersed. Okay, so yeah, I mean, the range is a very simple measure of variation. Okay, just take the difference between the smallest and largest number, and you can compare the ranges. All right, so of course, the data set with the largest range would be more dispersed, right? But the thing with the range, the problem with the range is that the range actually doesn't tell us how much the other values vary from the mean or from another. Okay, so it's not really, I would say it's not really, sometimes it's not really useful. You can have like two data sets with the same range, okay, but like one data set would be more dispersed. So yeah, so what I'm saying is that, so the problem with the range is that it doesn't tell us how much, so the range, it doesn't tell us how much the other values, the data values vary from the mean. The data values vary from the mean. Okay. Yeah, so yeah, anyway, so that's for the range. That's our first measure of variation. Now, next, so we have the main and the most important measure of variation, which it's called the variance and the standard deviation. So number 2. So we have the variance and standard deviation. So the idea, guys, is that this variance or standard deviation, they give actually a measure of the deviation of the data from the mean. So the idea here, so this variance or standard deviation, the idea is that, so the variance and standard deviation okay, they give actually a measure, of the deviation of the variation deviation of the data from the mean. And again, guys, the mean is supposed to be the expected value. So when you have data, we have a data value, we have a number. So what you expect as a number is the mean, is the average. That's what you expect, okay? And so this variance or standard deviation, they're gonna measure the difference of the data value from the mean, okay? So of the data from the mean, okay? So, okay, so I'm going to show you how to compute, of course, the variance and the standard deviation. But again, so the thing is, So what you have to keep in mind is that the spread of the data around the mean. So the spread of the data around the mean is going to be as small if this standard deviation or variance is small. So the spread of data around the mean is gonna be small if the variance or the standard deviation is small. If standard deviation is small. Is small. Okay. And it's going to be this spread of data around the mean is going to be large if the standard deviation is large, of course. So, and the spread of the data around the mean is large if the standard deviation is large. Deviation is large. Okay. Anyway, so I'm going to show you now, of course, how to compute the variance and the standard deviation. Okay. So now the question is, so how do we compute the variance and the standard deviation? So I'm going to use the example we had before, the flower diameters, and so variance and standard deviation. All right. So at the same time, I'm going to give you an example. So I'm going to give you an example, guys, and at the same time, I'm going to give you explain the notation and the definition. Okay, so so here example, and at the same time, I'm going to introduce some notation. Okay, and at the same time, I'm gonna give you some definitions. All right. All right, so as I said, we're going to go with this example, the flower diameters. So we have this again, the sample of flower diameters. Okay, flower diameters in inches, of course, in inches. All right. So the units here are kind of important. Okay, so we are using inches here, and let's take the hybrid. Let's take the hybrid B, and then we're going to compute the same thing for the hybrid A, and then we're going to compare. Of course, we're going to see the difference between the standard deviation and the variance. Okay, so let's do it. I mean, we can do it for, well, let's start with the hybrid B, and then we're going to do it for the hybrid A. And then we're going to compare the standard deviations of both hybrids. So yeah, the hybrid B, we said we have like, 5, we had 6 flowers, right? The first flower has diameter equal to 5 inches. Second, it's again 5 inches. Third, 5. Fourth flower has 6 as diameter, 6 inches as diameter. 7 inches as diameter, and the last one has 8 inches as diameter. All right. So we said first. So one, I'm gonna need the mean to compute the variance and the standard deviation. So first, let me just explain again. So the x So X supposed to represent the data value, right? The X represents the data value. Okay, so like in this example, X would be 5 or 6 or 7 or 8. Okay, so here X can be equal to 5, is 5, or X can be equal to 6, or X can be 7, or X could be 8. Okay, so when I say X, it's just your data value. It's just a number from the data set. Okay, that's what I mean by the X. X bar, of course, we know what's X bar. X bar is supposed to be the mean, right? The average. So 2. So 2, I'm gonna need the mean. So X bar, this is your, so this is equal, of course, to the sum of the X values, the sum of the data values over the size of the sample, right? This is your mean. So that represents the mean, or what you expect, right? The mean, that's the data value that you expect. Okay, and just to remind you, the N, this is the size of the sample. All right, so in our example here, in our example, the mean would be like, as I said, I mean, we computed the mean, right? So that would be like 5, plus 5, plus 5, plus 6, plus 7, plus 8, and then the whole thing divided by the size of the sample. We have 6 flowers, so we need to divide by 6, right? So this is just 36 over 6. And as I said, the mean is going to be equal to 6 inches, right? Okay, so now, guys, next, to compute the variance and the standard deviation. So we're gonna need the sum of X squared. So phi. So in the third step, well, we're gonna need so the sum of X squared. Okay. So you just take the square of the data values. So the sum of the square of the data values. So like here in this example, right? So that'll be like the first data value is 5, right? So that'll be 5 squared plus the second data value. Okay, it's again 5, so that's 5 squared plus another 5 squared plus a 6 squared plus next value, it's 7 squared plus 8 squared, right? So like in this example, so of course, you know how to compute this, all right? Just to use the calculator, you can just say, well, so like in this example, you have like a 5 squared, 5 squared, it's like 25, 25, 25, 36, right? 49, right? Plus 8 squared. 8 times 8, that will be 64, right? So this is equal to, let me see, I got the value somewhere in my notes. Plus 4, and this is 1. So I think, yes, here it is. Yes, it's 224. Okay, so that's what I mean by the sum of X squared. Just take the square of your data values. Okay. Now, next, guys. So we have the sum of x squared. Next, we're gonna need the sum of the x, the sum of the data values, and then we will squared. So number 4. In number 4, we're gonna need the sum of the data values, okay, and then squared. So this is different from number 3. So in this number 4, we're gonna take the sum of the data values, and then we take the square. Okay, so it's like, so this is like first data value, it's 5 plus 5 plus 5, right? Plus 6 plus 7 plus 8, all right? And then once you do the sum, then you take the square. Okay, don't forget your PEMDAS rule, guys. So parentheses first, you have parentheses and then exponent, right? So here in this case, like in between parentheses, we have like, 5 plus 5, 10, 15, 21, 28 plus 8, that's 36, right? So this is like 36 square, 36 square, and 36 square would be equal to, so this is 36. So 36 square, I'm sorry. So this is just, this is just 36 times 36, or 36 square. So this would be equal to, let's see here. So let me just check my my notes. So
1,296.
yeah, thank you. I didn't actually. I have trouble with my notes. 1,000 and sorry.
Oh, 1,296.
296. Thank you so much. Appreciate. I have trouble with my notes, I think. All right. So, okay. So now, the last step, number 5, or not the last step, but there is one more step. So in number 5, number 5. So we need to compute the variance or the sample variance. So I'm going to give you the definition of the sample variance here. So this definition right here. So the variance or the sample variance in this case, so the variance, the sample variance so it's denoted by, the textbook or the literature, the sample variance is denoted by S square. It's S square, okay? Why the square? Because for the standard deviation, we're gonna take the square root of this. The standard deviation is the S, and the sample variance is just the square. So so the sample variance is the S square, and it's actually equal to the sum of the x squared minus, and then you have this sum of x's squared divided by n here, and then the whole thing divided by n minus 1. Okay, so this is the formula for the sample variance or the variance. Okay, so like in our example, this is a sample variance. So S squared would be equal to, so first guys, we have the sum of x squares, right? So this is, we computed this in the step number 3, right? This is just right here. So this is in the step number 3. Okay, step 3. Okay. So as we said, this would be, so here it's 224. Okay, so this is 224 minus, now we have like a fraction. So we have this sum of the x, the data values squared. So this is what we have in the step number 4. So this is this thing here, this top here. This is what we had in step number 4. Step 4. Okay, so in step 4, we had 1296. So here, this is 1296 over n. Okay, so it's a fraction there. It's divided. We just divide the 1296 by n. Okay, and that's, of course, that's the size of the sample. We had 6 flowers. I mean, we had like 6 data values or 6 numbers. So n here is just 6, right? So n is 6. Sorry, n is 6 right here. And then the whole thing. So just be careful. We have to divide by not n, but we divide by n minus 1. Okay, so just be careful here. It's n minus 1. It's not n. So n minus 1, of course, n is 6. So 6 minus 1, it would be 5. So here we need to divide by 5. Okay, so again, n here is equal to 6. That's because we have 6 flowers. All right, so let's compute this thing. So just first, we have to do the top. So we have like, so this sample variance would be like 224 minus, and then we have to divide this 1296, divided by 6. So that'll be equal to 216. So this is 216. All right, and then the whole thing divided by 4. Okay, so again, I got the 216 from this thing right here. This is 216. Okay, now of course, 224 minus 216, that will be equal to 8. So that's 8 over 3. 8 over 5. And 8 over 5 would be 1.6, right? If I'm not mistaken, yes, 1.6. Okay, so yeah, the sample variance. So the variance in this case, so this S square is equal to 1.6. Okay, now as I said, there's a square because we need to take the square root of this square. So the standard deviation, so the fine answer, what we need here is the square root of this thing. So then the last step number 6. So step number 6. So in the step number 6, so this is definition of the standard deviation. Definition of the standard. So the standard deviation, which is denoted by S, right? So the sample variance, it's S squared, okay? The standard deviation, it's S. And S, of course, that will be, it's just the square root of S squared. Okay, because the square root and the square, they kind of cancel out, right? So it's just S. The square root of S squared is just S. So in this example, so our S, our standard deviation, so standard deviation S, S would be square root of 1.6. Again, 1.6, that's the number I got, that's the answer from the step number 5, right? This here's 1.6. That's my S square, right? That's 1.6. So my S, my standard deviation would be square root of 1.6, which is actually equal to so this is equal to 1. So S, final answer here. So our standard deviation S is equal to 1.26. So this number, actually, we'll see in a couple of minutes. So this number is going to measure the variability of your data set. Okay, so this is, oops. It's actually 1.26 inches. Okay, the units, of course, here it's inches. We need to keep the units here. I mean, this is 1.26 inches. Okay, so yeah, as I said, so this number.
Sorry, Professor, I'm
yes.
sorry. So
Yeah,
when you
please.
said the standard divided by X equal like root 1.16, why you get the 126 inches? So I don't get it. Can you repeat, please?
Oh yeah. No, I just take I took the square root of 1.6. 1.6 is my decimal, right? That's my number, 1.6. I just took the square root of 1.6. But of course, you need to use the calculator for that.
Okay.
If you have your calculator in front of you, then you can just press like the square root, this symbol, I guess. You can see this symbol on your calculator, right? This square root, and then press 1.6. So that will give you this 1.26. Probably, I mean, when I meet you in person on Wednesday, I can show you with your, because we're gonna do like a lot of computations with the standard deviation and the variance. So I mean, if you have a trouble with the calculator, I can help you with that like on Wednesday. Yeah, but all you have to do is just to press the square root and then press 1.6. So that would be the 1.26. Like, so here it's like saying square root of 4, it's 2, right? Because 2 times 2 is 4, right? So here's the same thing. So what I'm saying is like 1.26 times 1.26, that will be this 1.6. Okay, it's just the square root. Yeah, so I was saying this number, so this standard deviation is going to measure the variability of your data set. So like in this example, so let me just write down here. So this number here, so this standard deviation is going to measure measures the variability of your data set. Okay, so in other words, if this number here, if this standard deviation is small, okay, if the standard deviation is small, it means that the spread of the data around the mean is going to be small, or in other words, your data set is going to be constant in some sense. Okay, so what I'm saying is, so if your data, or if your standard deviation is small, so if this number here is small, it's a small number. Okay, then the spread of your data set or data values of your data values is going to be small compared to the mean is of data values is small around the mean. So in other words, your data values, they're going to be very close to the mean. in general, around the mean. So in other words, your data values, so the data values, if your standard deviation is small, data values, they're gonna be are close. They're gonna be close to the mean in general. In general. Of course, you can have probably some exceptional values, but so in general, if you take a number in your data set, and your standard deviation is small, if you take a number, then your expectation is that the number is going to be kind of close to the mean. All right. So like here in this example, my standard deviation is actually 1.26 inches, which is kind of a small number. I mean, we're gonna do another the other hybrid, the hybrid A, and we can compare the two standard deviations. But in this example, for the hybrid B, the standard deviation, which is 1.26, which is kind of small number. I mean, it's kind of small number, right? So which means that if you take a data value, then in general, your data value is gonna be very close to the mean or the average. So remember, guys, in our example here, in this hybrid B, the mean is 6, right? We said X bar, the mean, the average is 6. So when I take any data value, what I expect is that my data value is going to be kind of close to the mean. Okay, so as you can see here, 5, it's close to 6. Well, 6 is just equal to 6, right? It's just equal to the mean. 7 is also kind of close, kind of very close to the mean, which is 6. Then the same for 8. Okay, so your numbers or your data values, when the standard deviation is small, your data values are kind of very close to the mean. They're not dispersed. Does this make sense to you guys? So you see, this standard deviation is very, very useful. And we're gonna see like, okay, what we can do now is let's compute yeah, let's compute the standard deviation for the hybrid A, and we're gonna compare the two standard deviations and see which standard deviation is gonna be larger. Okay. And so what do we expect here, guys? Remember, the hybrid, in the hybrid A, okay, let's just, so just remind you what we had. So we have this hybrid B, first hybrid A. The hybrid A, the values are, what are the values of hybrid A? Yes, it's 2, I think, 3, 3, 8, 10, and 10, if I'm not mistaken. Yes, I think so. Right. This is again, this is just the diameter of your flower. So in the hybrid A, in the hybrid B, we have, as I said, what was the values of the 5? I think, yeah, 5, 5, 5, 6, 7, and 8. Right. So we said hybrid A has more variation, right? So when you look to the numbers here, data values, you can say, well, hybrid A has more variation than hybrid B, okay? And so we just computed the standard deviation for the hybrid B. So the hybrid B, the standard deviation of the hybrid B is it's 1.26 inches. Okay, so what do we expect? Do we expect the standard deviation of hybrid A to be larger than the standard deviation of hybrid B, or less than the standard deviation of hybrid B?
Higher.
Higher, absolutely. Thank you. Excellent. Yeah. So that's exactly the idea. So because hybrid A has more variation, has more variation, right? Then we expect the standard deviation of hybrid A to be larger of hybrid A to be larger because it has more variation, to be larger than standard deviation of hybrid B, larger than standard deviation of hybrid B. Okay, so here's an exercise for you guys. Please try to compute the standard deviation of hybrid A. Okay, so I just compute the standard deviation of hybrid B. So in this exercise, okay, let's compute. So then we can compare to the standard deviation of hybrid B. So please try to compute standard deviation of hybrid A. The standard deviation of S of hybrid A. And remember, guys, both hybrids they have the same mean, right? Both the mean was, I think, was 6, right? So they have the same mean, but of course, actually they're going to have different standard deviation. All right, guys, I'm going to give you a couple of minutes to compute the standard deviation of hybrid A. So just try to follow. I mean, you have the formula, right, for the standard deviation. Okay, I can probably go up. Yeah, just try to follow the steps and compute this standard deviation. Sorry. Yeah, so I'm gonna just probably remind you this. Oops. Just remind you the steps, guys. I mean, my advice for you, of course, is to go step by step because the formula is kind of well, a lot of terms on the formula, so it's better to go like step by step. Yeah, just remind you the steps. So first, let's see right here. Yeah, so first I would say, so step one would be to compute the sum of the step one would be to compute the sum of the squares of x. The step number two would be to compute the sum of x the data values and then take the square of the whole thing, of the sum. And then step number 3, you can probably try to compute the variance, the S square, the variance. So that would be the sum of x squared minus this thing here divided by n, and then the whole thing divided by n minus 1. Okay, that will be your variance, and then the standard deviation is, the S would be just the square root of S squared. Yeah, so again, guys, just be careful. This is the sum of the squares. And this is the square of the sum. Um, Again, so I know it's easy to get confused. I mean, with this formula. So we will do one more example, one more exercise. So, I mean, take your time, guys, because this is, I mean, the standard deviation, and this is really important. We're gonna use it later in the next sections. So we need to know how to compute this. Take your time. Well, I mean, and of course, if you have questions, I'm here to answer them. Um, um, did anyone get the answer? The standard deviation of this hybrid A?
Yes.
Yes. So what's your answer? I think I have the
I believe it's 6.6.
6.6. I don't think so. I mean, the answer I have is 3.74. So yeah, I don't think it's correct. So I think the answer, the final answer should be 3.74. So can you check again all the steps? So what's your S square? What did you get as S square? Final answer for S square? The variance? This in the step number C? The step number
43.2, but I see where I went wrong at now.
Okay. Yeah, of course. I'm gonna go over. Juliana, I'm gonna go over this exercise. Sure. Just gonna give you. I'm gonna give you a little bit of time to think. Yeah, no problem. I'm gonna give you a little bit of time to think about the. I mean, to do these computations because they are important and you need to know how to do them. So, yeah, sure. I'm gonna go over the exercise. That's no problem. And yeah, just take your time with the computations. Did anyone get 3.74 as a final answer? Excuse me. Okay, guys. I mean, anyway, we're gonna do one more example. So again, because you need to know how to do this computations. So I'm gonna go over this first, and then I will give you another different example or different exercise. You're probably having trouble probably with the step number 3, I guess. Okay, I'm gonna give you, let's say, 3 more minutes. All right, guys. So yeah, let's do this exercise together, and then okay, I will give you a similar exercise, so then you can try to follow the same steps. All right. So well, first, did anyone get the 3.74? No one.
I did.
You did?
Yeah, when I did it over, when I found my problem at, I got 3.74.
Perfect. Perfect. Sounds good. That's perfect. That's good. Because again, these computations sometimes they kind of sometimes they're kind of a mess. So yeah, that's perfect. All right. So okay, let's do this together. So so as a first step, let me just remind you the data values, right? So we have this. So hybrid A, we said the flower diameters in the hybrid A. I think we had, let me see, we had 2. Second flower diameter is 3 inches, 3 inches, 8, 10, and then 10. Right? Okay, so yeah, let's do this. So first step, step 1, the sum of the squares. So you take the square of the first number, that will be 2 square, plus the square of the second number, 3 square, plus, sorry, I forgot to, so this is where I denote by sum of the x square. So that will be 2 square, plus 3 square, plus 3 square, plus 8 square, plus 10 square, plus 10 square. All right, so 2 square, of course, is 4. This is 9, 64. 10 squared, 10 times 10, that's 100. And then again, 100, right? So this is 286, if I'm not mistaken, right? So this is equal to 286. I hope everyone got this 286 in the first step. So, okay. Now, second step, step number 2, it's the sum, the square of the sum. So, from this rule, right? So we do first what's inside the parentheses. Inside the parentheses, we have the sum. So we do the sum first, and then we take the square. So that'll be like 2 plus 3 plus 3 plus 8 plus 10 plus 10, and then the whole thing squared. Okay, so inside the parentheses, we have like 2 plus 3, that's 5, plus 3, that's 8, 8 plus 8, that's 16, 26, and then 36, right? So this is just 36 square, right? And 36 square, we said it's 1296, right? This is 1296. Okay. Now, step number 3. So in this step number 3, you can compute the variance. Step number 3, the s square. Okay, so let me write down first the formula. So it's the sum of the x squared minus sum of the x squared over n, and then the whole thing divided by n minus 1. Okay. First, the sum of the squares, this one here, this is from the what we got in the first step 1, right? The 286. Okay, so this s squared, so it's going to be equal to, so this is 286 minus, and then here we have a fraction. Okay, just be careful. There's a fraction in the top of this fraction. There is this the square of the sum. So that'll be from the step number 2. That's the 1296. So minus 1296, and then you have to divide by the size of the sample. Right, the size of the sample is 6, so we have to divide by 6. Right, this n here, that's the size of the sample we have, or the number of data values. So we have 6 of them, and then the whole thing divided by n minus 1. N again is 6, so that'll be 5. Okay, so when you have such a fraction, guys, first you have to divide this thing here. So first you divide this thing here. Okay, this is the first thing to do. First thing to do. Okay, divide this 1296 by 6. Okay, so 1296 over 6, that's again 216. So this is so this is variance, It's 286 minus 216, right? Over 4. Sorry, over 5. Right? Now, the next thing to do is the top. We have to finish the top, the numerator right here. Next thing do. Okay. So we subtract 286 minus 216. All right, that will be equal to 70. So yeah, that's 286 minus 216. That'll be 70 over 5. Okay, and then 70 over 5, that'll be equal to 14. Okay, any question, guys, so far? Okay, now questions, and then that's our variance. Now the standard deviation, so find the answer. So the standard deviation, step number 4. So your S, your standard deviation, S, it's just the square root of this S square. So in other words, your S, the standard deviation, it's the square root of 14, which is actually 3.74 inches. Okay. And as we expected, guys, as you can see, the hybrid A, so that's here's so the remark is the following. So in the hybrid A, and as we expected, so hybrid A, its standard deviation, it's actually 3.74. Hybrid B, inches. Hybrid B, the standard deviation, we said it's 1 point, I forgot, 1 point something, was
1.26.
26, thank you, I appreciate it. 1.26 inches. All right. So as you can see, guys, so the hybrid A, so the standard deviation of hybrid A is larger than standard deviation of hybrid B. So standard deviation of A is larger than standard deviation of B, which means B. So as we said, the hybrid A has more variation. Hybrid A has more variation, or in other words, the spread of the data in the hybrid A around the mean is larger than the spread of the data around the mean in the hybrid B. Okay, so in other words, the spread of data in A is larger than in B, than the spread of data in B. Okay, and that's exactly what we expected, right? Yeah. Any question, guys? Anyway, so you see why this standard deviation is useful. So you have like 2 samples, you can compute their standard deviations, and from the standard deviation, you can say which data set has more variation, right? All right, so let's do another exercise because again, as I said, because we're going to use this next section, so it's kind of an important thing. You need to know how to compute this standard, variance and standard deviation. So let's do another exercise. Exercise number 2. And yeah, you need to make sure that you get the right answer. I'm going to give you the answer of this exercise, and just make sure that you get the answer, guys. Yeah, so exercise number 2. Okay, so let's say you have the following sample data. Let's say 23. 17, 15, 30, and 25. Okay, so please try to compute the standard deviation. S of the sample data. So this is, I think this exercise it's from the textbook. It's exercise, I think 13, page 116. Okay, so this is from the textbook, actually. So it's from the textbook. Anyway, yeah, so I'm going to give you a couple of minutes, guys, to compute the standard deviation, and make sure that you get the correct answer. So the answer for this, you should, the answer, oops. So the answer would be S should be equal to it's, I think, 5. What's the answer? Yeah, I think this should supposed to be 5.44. Okay. Sorry, it's a 6.08. Sorry, it's actually 6.08. That's a different exercise. This is 6.08. Okay. Yeah, so after this exercise, guys, I'm gonna probably introduce, yeah, I'm gonna just mention, so there's a different notation when, so this, for this variance or standard deviation, right? We use this notation S and S square, but this is when you have like a sample data. In the case of a population data, we have like a different notation, right? Remember, like for the mean, for the sample mean, we use this X bar, right? And if you have a population mean, remember we use this mu for population mean. So the same thing for the standard deviation. So the standard deviation, we have different notation when you have population data. Anyway, yeah, after the exercise, I'm gonna we're gonna talk about the coefficient of variation. The thing is, this standard deviation depends on, the answer depends on units, right? Like in this flower diameter, the standard deviation, it's like 1.24 inches, right, etc. So you can use that to compare, like if you have two samples of flower diameters, right? Because we are using the same unit, it's inches, right? So you can compare them. But then the thing is, if you have like two sample data where you use like different units, like in the first data, in the first sample, you're using, I don't know, let's say kilograms, and in the second data, you are using inches or feet or anything different, okay? The standard deviation depends on the unit, so you cannot really use the standard deviation to compare the two data values. But so I'm going to introduce this coefficient of variation, and with this coefficient of variation, you can compare measurements of different populations where you use like different units. Okay. Anyway, I hope you got this this answer 6.08. I mean, does anyone have like a question or a trouble getting this answer? Well, I hope not, because as I said, we're gonna compute a lot of standard deviations. So we need to really know how to compute this thing. Okay, I guess, yeah, I'm gonna go over this exercise. I hope you got the answer, but let's do it. Okay, so as a first step, step one. Okay, so I mean, as usual, so in the first step, we're gonna compute this the sum of x squares. X squares. So this is like 23 square. Sorry, 23 square plus 17 square. Next data value is 15, so that'll be plus 15 square plus 30 square plus 25 square, right? So then 23 square would be equal to, so this is 5, I think 25, plus 17 square, that will be 285. All right. Next, 15 square, that will be 225. 30 square, that will be 900. And 25 square, that will be equal to 625. All right. So the sum here would be, so it's, let's see, so it's 525, sorry, 529 plus 289, right? Plus 225 plus 90 plus 625. So that'll be equal to, this is actually 2,568, if I'm not mistaken. Right. Okay, so that's for the first step. Step number 2. So we need the sum of the square of the sum. So that would be like 23 plus 17 plus 15 plus 30 plus 25, and then the whole thing squared, right? So 23 plus 17, that's 40, plus 15, that's 55. Sorry? What's the answer?
110.
110, thank you. I appreciate it. Square, and then of course 110 squared, that will be equal to 12,100. Okay. Thank you. Sorry, it's square there. For some reason, this is a square, of course. Sorry. That's a square. Now, step number 3, I can compute my standard, my variance first. So my S square, so that will be the sum of the x squared minus the square of the sum over, this is divided by n, the size of the sample. We have 5, we have 5 numbers, 5 data values. So you're gonna divide this by 5, and then the whole thing divided by n minus 1. So that's 5 minus 1, because we have 5 numbers. So 5 minus 1, it's 4. All right, so this is equal to, so your S squared, this is sum of the squares. That's in the first step. That's the 2,568. So this is 2,568 minus the square of the sum. That's from the step number 2. This 12,100. So minus 12,100 over 5, and then the whole thing divided by 4. So first thing to do, guys, is to divide this 12,100 by 5. So first thing to do is this thing here. Okay, so this 12,100 divided by 5, that'll be equal to 2,420. So this is equal to, so we have 2,568 minus, this is 2,420 over 4. So this is equal. Now we have to subtract in the top, this thing here.
It's 144.
Yeah, thank you. As you said, so it's 148, right?
Yeah.
Thanks. So that's 148 over 4, and so that will be equal to 37, right? If I'm not, yes, 37, absolutely. All right. And finally, we're gonna get our standard deviation. So then that will be, oops, step number 4, our step number 4. So the standard deviation S so S is just the square root of this S square. So that will be square root of the 37, which is exactly, I think, the answer. This the 6.008, not phi. Actually, it's I think it's 6.08. So why do you get 6.3? Did you say 6.3, right? You said 6.3, right?
No, I said 6.08.
Oh, 0.8, sorry. For some reason, I heard 3. Thank you. So yeah, units, of course, here. All right, any question, guys? Perfect. All right, so yeah, before the next thing, the coefficient of the variation. Yeah, I'm gonna just say a couple of words about the, before the notation, the formula. So in the literature, guys, or the textbook, there is actually different formula for this standard deviation. And actually they're equal, they're the same thing, but it's just a different, it looks different, but actually they're just, they are equal. So yeah, let me make a couple of remarks here. So first remark is that, so our formula for the standard deviation or the variance, we said, so the formula we are using is, so this one, all right, here for the variance, the S square. So we said like it's sum of X square minus, and then you have like sum of X square over N, and the whole thing divided by N minus 1, right? That's what we are using to compute the variance or the sample variance, right? Now, in the textbook or in the literature, there is a different formula which looks different, but they are the same, they are equal. I mean, you can prove that they are equal. So which is the following. So in the textbook, or in the literature, there is another formula, which is the equal. There is another formula for the variance, which is actually given by sum of the X minus X bar squared over the whole thing over N minus 1. Okay. So this is S squared, of course, the variance, right? So, both formulas are equal. They are the same. They are equal. They look different, but you can prove that they are equal. And we are using this one here because I think this one it's the easier for computation. Okay, so this one, I would say this one is easier, for computation. But both formula are equal. Okay, so if you find this one here in the textbook or in somewhere else, yeah, it's just the same formula. All right, they are equal. Okay, they are equal. The two formulas are equal. Okay. Yeah, another thing about the notation. So this is remark number 1. Yeah, so for the sample data, we are using S for the standard deviation. But in the case of population data, so remark number 2. So remark number 2 So the simple data, we use S. The standard deviation is denoted by S. So it's S. For the population data, the population data, the standard deviation is actually denoted by sigma. So for population data, so when I say population data, guys, I mean that all data values, they represent all the population, not just a sample, but all the population. Okay, so population data, the standard deviation is actually denoted by sigma. So here's sigma. Okay, so this is sigma is this is a Greek letter, of course. This is a Greek letter. Okay, actually, as I said, the summation, guys. So this is a capital sigma, and this one is the lowercase sigma. This is capital sigma. This is capital sigma, and so this one is lowercase sigma. Okay. Anyway, just for your information. Okay, so this is standard deviation is denoted by sigma for the population data. All right. Yeah, I think yeah. So we are done with this sample, the standard deviation and the variance, the sample variance. Yeah. So next, as I said, I'm going to talk about the coefficient of variation. So next, is there any question first, guys? What's next after? Oh, sigma. That's sigma, Juliana. So this is yeah, it's a Greek letter. It's called sigma. This is called sigma. I'm gonna probably just erase this thing here. Yeah, it's denoted by sigma. Yeah, it's a Greek. It's a Greek letter. Okay. All right. Yeah. So, any question, guys, before moving to the coefficient of variation? Okay, perfect. So the thing is, the problem with the standard deviation is that the standard deviation depends on the units, right? Like in our example, the flowers, diameters. So the standard deviation, it's the units are inches, right? So we are using units. So the standard deviation depends on the units, right? Now, if you want to compare two samples, sample data using different units, you cannot really do it with the standard deviation because if you are using two different units, then you cannot compare two things using two different units. So that's why we're going to use this coefficient of variation because coefficient of variation is going to be independent of units. So you can compare measurements of different populations, okay? Yeah, so so next, so we had the range, we had the standard deviation of standard deviation and the sample variance. Next, we have the coefficient of variation. Okay, so the problem, as I said, so for example, guys, let's say we have the first data represents so this first data, oops. So let's say this first data represents again the flower diameters. Okay, so let's say you have, I don't know, let's say a 6, 7, 8, 8, 9, 10, and 11. Okay, and you have a second data which represents the age of some, let's say, professional soccer players. Okay, the age of soccer players, like I don't know, in some team. So let's say you have I don't know, like 30, and then 31, 31. Fourth player, his age, let's say he's 32 years old. Next player, I don't know, he's 34 years old, etc. So we have, let's say, same 35, and then 37. Okay. Anyway, so the thing is, here in the first data sample, here with the units, so here the units are inches. All right, and here the units, of course, are years, right? Okay, so we are using two different units, and that's a problem. So if you want to compare, so we want to compare the spread of the two data samples or data sets. Okay. So of course you would like to use the standard deviation, but the problem with the standard deviation is that the standard deviation depends on the units. There's a problem, so we cannot really use the we cannot really use the standard deviation because well, the standard deviation depends on the units. So you cannot compare something which is like where you are using like inches to something where you are using like different units, like years or kilograms or wherever. Okay, so because we are using because the standard deviation depends on the units. The standard deviation depends on the units, and we cannot compare two different units. Right, two different units. You cannot compare kilograms to inches, right? Or years to inches, etc. They're two different units. Right, so that's why we're going to use this coefficient of variation. So unlike standard deviation, this coefficient of variation is going to be independent of units. So unlike S, the standard deviation, the coefficient of variation is going to be variation is going to be independent. It's going to be independent of units. So if it's independent of units, then you can compare two samples with using different units. Okay, is actually independent. Okay, so it's because it's independent of units, then you can compare measurements of different populations. So then we can compare measurements of different populations. All right, guys, I'm gonna give you, I guess, the formula for this coefficient of variation. And actually, we use the standard deviation and this, so of measurements of different populations, of course. That's what I meant, of different populations. Of different populations. All right. All right, so what's the formula? I'm going to give you the definition of the coefficient of variation, right? And then we can have a couple of examples, so you can see how we can use this coefficient of variation to compare data sets, right? How much time do you have? Oh, we have like 2 minutes. Well, I don't think, I mean, 2 minutes I can like, define the coefficient of variation and give examples. So yeah, probably I'm gonna do this next time, Wednesday. Okay, so on Wednesday, next time, so we're gonna see how this coefficient of variation, okay? Of variation. All right, guys, I guess I'm gonna stop here because we don't have time to introduce the coefficient of variation and do examples. So I'm gonna just do this on Wednesday. All right, see you on Wednesday in person. Thank you for listening, and good night, everyone. Thank you, guys.
Thank you, Professor.
Good night.
Thank you.
Hi, Professor.
Good night, Professor.
Good night. See you on Wednesday.